Welcome to our class notes on electron configurations 4-11. If you remember, in Unit 4, we are learning to represent the placement of electrons according to the quantum mechanical model, the fifth model of the atom. Schrodinger's model also contributed significantly to the model was Heisenberg, and it's sometimes called the electron cloud model because the orbitals are three-dimensional. And when you take a look at the high places of the high probability, the shapes that we would find electrons, it looks like a three-dimensional cloud surrounding the nucleus. What are electron configurations? In general, electron configurations are any way of representing where the electrons have a high probability of being found. We said in this unit we would be discussing 4 of those. The first one we already learned about was orbital notation. And this is an orbital notation right here. If you remember with the orbital notation, we had boxes representing the orbitals, or a line is sometimes used to represent the orbitals, a line meaning just the bottom part of the box. And they had electrons were represented by arrows. An arrow pointing up was an electron spinning one way. An arrow pointing down is the electron spinning the opposite way. And then you needed a number of boxes that equaled the number of orbitals found in the sublevel. For the S sublevel, we already know there's 1 orbital. The P is made up of 3 orbitals. Each orbital holds 2 electrons, so the S can hold 2 electrons. The P can hold a total, the P sublevel can hold a total of 6 electrons. And if you remember, the Ds were made up of 5 orbitals holding a total of 10 electrons, and the F sublevel was made up of 7 orbitals holding a total of 14 electrons. And we learned to place the electrons in an order, starting with the lowest energy levels first, according to the Aufbau order of filling. Now, when we did the orbital notations, we did not spend much time talking about Aufbau order of filling because you were given the order of filling underneath the boxes. So if we did oxygen, for instance, you were told we had a 1s box first, then the 2s, then the 2p. Above the boxes, or the orbitals, we put the orbital numbers. That's the 3rd quantum number right there. And then the 4th quantum number was designated by the spin of the arrow. An arrow up was the plus half spin, an arrow down was the minus half spin. So the orbital notations did a great job of representing really the 4 quantum numbers. The first quantum number was the number that we see underneath the orbital boxes, underneath each sublevel. So the energy of this box right here, the principal quantum number is 1. The second number is the number code for the S shape. S, if you remember, the second number was a 0. If you were in a P sublevel, the second number was a 1. If you were in a D sublevel, the second number was a 2. The F sublevel, the second number was a 3. The third number is above the box. That's the magnetic quantum number. And then the 4th quantum number was the spin. Arrow up, plus half, arrow down, minus half. So an electron, for instance, right here, its first number would be 1. First quantum number is 1. Second quantum number, since it's in the S, is a 0. The 3rd quantum number, since it's in the 0 orbital, is a 0. And if we're talking about that electron right there, the 4th quantum number would be a plus half spin since the arrow was going up. So orbital notation, there was a lot of information we could get from an orbital notation. The second type of electron configuration that we're going to learn to do is called an electron configuration. This one's actually named after the process of showing where electrons are in general. This is a very, very frequently used way of representing where electrons are. Now, chemists tend to be a little bit lazy. After a while, they get tired of drawing boxes or lines and arrows and putting in the orbital notations, putting in the numbers above the boxes and the numbers below the boxes. Again, the superscripts telling you how many electrons there are in each of those sublevels. So this little 2 right here is telling us there's 2 electrons in that box. This 2 is telling us there's 2 electrons in that box. This 4 is telling us there's 4 total electrons in all of those 3 boxes added up. So what chemists decided to do was just shorten this and only give what is underneath the sublevel boxes. This part underneath is called the electron configuration. So when we do electron configurations, you do not draw the boxes or lines representing the box. You do not put the numbers above the boxes, and you don't even put the arrows in. So the electron configuration of oxygen would be 1s2, 2s2, 2p4. Now, how do we know when you do an electron configuration, you're not going to be given all of this stuff right here? You're not going to be given the 1s, the 2s, the 2p. You were given that when you did the orbital notations, and we were just getting familiar with how to do that. The reason you do not have to be given the order of filling is, as we are about to learn, the periodic table gives you the order of filling. Where these numbers come from, the 1s, 2s, 2p, now that is a great story indeed. And it takes us back to where we began this unit, quantum numbers. Let's go back and take a look at our notes from quantum numbers. The notes we're looking at is in your 4-5 note packet, and that's where we started off with models of the atom, a brief history, review of models of the atom, and then we came to Model 5, Schrodinger's quantum mechanical model, which introduces the 4 quantum numbers. Those order of filling, the 1s, 2s, 2p, relates directly to the quantum mechanic model and the 4 quantum numbers. So let's take a quick look again at the principal quantum number. That is the number that is abbreviated by N. That is the number that Bohr knew about. Bohr said that there were 7 levels, energy levels, or 7 shells to the atom. Now, what Bohr didn't know, however, was that each level or shell actually was made up of more different numbers of sublevels. If you remember, the first level had 1 sublevel. The second level has 2 sublevels, the S and the P. The third has 3 sublevels, SPD. The fourth has 4 sublevels, SPDF. Fifth has 5, SPDF, and a G, which we do not need, etc. So there are 7 levels to the atom. Bohr knew that. What Bohr didn't know, and where quantum mechanic models build upon Bohr's model, is the fact that electrons can occupy different numbers of sublevels, and the number of sublevels corresponds to our first quantum number, n. So n is allowed to be 1 through 7, and it will also tell you how many sublevels are possible on that energy level. So what is n's values allowed to be? We can see right here, n is allowed to be 1 through 7, theoretically up to infinity. Now let's take a look at the periodic table again. Here's our periodic table of elements that is in our class information section. We mentioned that n is allowed to be what? 1 through 7. Count with me for a second. I'm going to count the horizontal rows. 1, 2, 3, 4, 5, 6, 7. There are 7 horizontal rows, which we call periods on the periodic table. You might want to count these as 8 and 9. Well, those are not 8 and 9. In fact, we need to fold all of this up. This row right here actually fits right inside there where it says 57 to 71. This row right here actually fits inside there where it says 89 to 103. You see the 89 to 103. So all of this, when we go to 56, we come down and we go from 57 to 71. 87 and 88, we go to 89, that's down here through 103. At 103, we pop back up. So they've just broken this part of the table out and placed it down here. And the reason they did that is the periodic table would be a really long paper if all of this was jammed where it was supposed to be. So once again, we counted 1 to 7. There are 7 horizontal rows, which we call periods on the periodic table. That is the representation of Bohr's n, which is also the first quantum number in Schrodinger's quantum mechanical model. Now let's start moving on to the second quantum number, which we call the angular momentum quantum number, also called the azimuthal quantum number. And that's the one that's abbreviated by the cursive L. On this second quantum number, Again, the second quantum number relates to the first quantum number. If you remember, when we were on the first level, there was one sublevel. The second level had two. So the third had three, the fourth had four, the fifth had five. This is the second quantum number. Here's our first quantum number, the principal quantum number. What is the second quantum number allowed to be? It is allowed to be 0 to the first quantum number minus 1. So right here, our quantum number is 1. 1 minus 1 is 0. So the second quantum number has to be a 0. Now, they do not say quantum number 1, 0. What instead they say is quantum number 1, and they give a letter for the second quantum number. They would call that the 1s. On the second level, if our first number is a 2, our second number can be 0, always. As you see, there's always a 0 for your second number on every level of the atom. But we would take 2 minus 1, which is 1. So for our second quantum number, when you have a second quantum number of 1, you're said to be in the p sublevel. So there is a 2s and a 2p. We continue on. We've learned this. There's a 3s, a 3p, and a 3d. There's a 4s, 4p, 4d, 4f. Now, when we look at the different sublevels, if you remember, they were made up of different numbers of orbitals as well. The s sublevel was a spherical orbital, and it was only made up of one of them. The p sublevel is made up of 3 orbitals, sort of dumbbell or hamburger bun shaped. The d orbital was made up of 5 orbitals. The f orbital was made up of 7. 1, 3, 5, 7. How many electrons did each orbital hold? Well, if you think about it, each orbital only holds 2 electrons. So the s sublevel made up of 1 orbital would hold a maximum of 2 electrons. The p made up of 3 orbitals would hold a maximum of 6. The d made up of 5 orbitals would hold 10. The f made up of 7 orbitals would hold 14. So take a look at these things. The L, when the L is 0, you're in the s, holds 2. When L equals 1, you're in the p, 3 orbitals, holds 6. When the L equals 2, you're in the d orbital, d sublevel made up of 5 orbitals, holding 10. The f is made up of 7 orbitals, right there, holding a total of 14. So our numbers are 2, 6, 10, 14. The s holds 2, the p holds 6, the d holds 10, the f holds 14. What does that have to do with the periodic table of elements? Keep these numbers in your head again. 2, 6, 10, and 14. Looking back on our periodic table, our numbers again were 2, 6, 10, and 14. Count with me for a second. 1, 2. Look at this part of the table here. There are 2 columns. Then the pattern is broken. It drops down. It pops back up. Count with me here. 1, 2, 3, 4, 5, 6 columns on this part of the table. 2 is the S. 6 columns. Remember the 6, 3 orbitals, that's the P. Count with me here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 columns on this part of the table. What sublevel holds 10 electrons? The D. This is the S part of the table, the P part of the table, the D part of the table. Count with me right down here. Now remember, the LA and the AC actually fit in here, so we're going to count here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This part of the table corresponds to the F. This is the S block, the P block, the D block, and the F block. We're now going to talk in the next video how we can get Aufbau's order of filling from that information.